Hello everybody, hope you're doing well. This is paper 2 from November 2023 and this is time zone 1. Let's have a look at it and see what we can do. Okay, first question is a 12-mark question. Let's read it. Jan is investigating the shape of model helicopter propeller blades. A cross-section of one of the blades is shown, graphed on the coordinate axes. The shaded part of the cross-section is the area between the x-axis and the curve with equation y is equal to 4 root x minus x over 2 plus 1. And we have this given domain right here where they're saying for certain inputs where x is greater than 0 and less than 64. So what are these variables? X is the distance in millimeters from the edge of the blade, and y is the height in millimeters above the horizontal axis through the blade, as shown in the diagram. So what we have here is we have some function which takes x values, or our distance from or on the horizontal, and when we substitute or input these x values, we get a corresponding y value, or a height of a propeller blade as a function of our distance along the horizontal. So let's go ahead and see what they're asking us for the first part. The first part, part A, they're asking us to find the values of A, B, and C shown in the table. So we're asked to find A, B, and C right here. And these are all y values. So in this case, if we have an x value, an input, it looks like we should be able to just input these values into our function and then find the corresponding y value. So this looks to be, at the very beginning, a more straightforward input-output question. So to find the value of A, let's input the value of 16 into our function, for example, and then we'll do the same thing for 32 and 48. Okay, so let's go to the calculator and work out these values. Okay, so we have a function for square root. Our first value is 16 minus, we'll get a fraction here. This is going to be 16 over 2. And then it's going to be plus 1. Okay. Since we're here, let's do the other two as well. This is going to be 4 square root 32 minus, once again, 32 over 2 plus 1. And then the last value was 48. So let's go ahead and input that. 4 square root 48 minus 48 over 2 plus 1. Okay, so here we go. We have values for A, B, and C. Let's go back to the document and write these out. So for A, the value was 9. For B, the value was 7.627. So we're going to round that to 7.63. And for C, we had a value of 4.712. So let's round that to 4.71. All right, not a bad 3-mark question to start. If we wanted to, we could put millimeters, but just the value should be fine as well. Okay, we're then told that Jan uses the trapezoidal rule with 4 intervals to estimate the shaded area of the cross-section of the blade. Find Jan's estimate of the shaded area of the cross-section. So in this case, remember, often IB questions won't ask you to perform some kind of calculation just to test a discrete scale. Often we'll have a question that will lead to something else. So here they're asking us to find these heights at different points. That is to say at 16, 32, and 48. Actually, I'll do this a little better. 16, 32, and 48, to essentially divide up this horizontal section of this blade into 4 equal intervals. And then what we're going to do is apply the trapezoid rule. So what can we do? I guess we can first off apply the trapezoid rule, and then we'll give some background. There are potentially 2 ways to solve this. The first is the trapezoid rule, and then the second is using intuition and just finding the areas of the trapezoids themselves. So let's go ahead and use the trapezoid rule for the first part. So let's go to the formula booklet, and find the trapezoid rule. This would be under calculus, so topic 5. All right. Topic 5, there we have it, 5.8, the trapezoid rule, and here it is. We'll take this and actually we'll work with this on the other page and unpack what is actually going on and what this means and how we can use it. All right. So let's go down and write it here. So this is part B. And the trapezoid rule is given by, we're asked to find the sum of some function from some starting point to some end point, and then it's some function, and then the variable is x, so we just write it in terms of dx. And then this doesn't give us, the trapezoid rule doesn't give us the exact area, it's just an estimation. So we write these approximately equal to. And then we have our trapezoid rule. And it's 1/2 h, and we'll talk about what h is in a sec. Then we open up some brackets, and we have y0 plus yn, or y0 plus yn. And this would be the first vertical height, and this would be the vertical height at our endpoint. So vertical height at the start, and we can have the vertical height at the end. Maybe we'll label that. So we'll say y at start, and this would be the y value at the end. The nth is the very end. And then we have plus 2 times, and this will be y1 plus y2 plus all the values in between, all the way up to yn minus 1, which means the second last, essentially. So this would be the second last vertical height. Second last vertical height right here. And we also have this value of h. H essentially corresponds to, and this is actually maybe the better way to work out h, potentially. H corresponds to the size of our intervals. So we know this person, Jan, is going to divide this trapezoid, or sorry, they're going to divide this total area into 4 equal intervals. So how are they going to divide it? They're going to divide it into 4 equal sections, 1, 2, 3, 4. And h is the size of each of those intervals. So if we're going from 64, or from 0 to 64, our formula for h is equal to b minus a. Remember where we said in our original function, b was the endpoint, a was the starting point. b minus a over n. N is the number of intervals. It might be easier to think of this just in terms of intuition, as in b is our endpoint, a is our starting point, and just imagine, okay, what's the total distance that we need to travel? Well, if we're going all the way from 0 to 64, we travel a distance of 64, and we want to break that up into 4 equal intervals. So 64 over 4 is 16. So that means that the size of each of these intervals is 16 each. And that's going to be the value of h that our trapezoid rule takes. All right, so let's flesh this out a little more. So a was our starting point, b was our end point. We don't actually need these for our trapezoid rule, but this is just an intuition or idea of what we're kind of solving for. The sum under the curve, or the area under the curve. So 1/2 h, the size of these intervals, 16, and the y value at the start, so the height right at the very, very start. And when we're at 0, our height is equal to 1. So let's go put that in our formula. 1 plus, and this value right here was the height at the very end, or the y value at the end. And we said 64. 64 has a height of 1, and that's given to us right here at the bottom. Plus 2 times, and these are all of the intermediate heights. So we can write that, I suppose. These are the intermediate values for the heights at these given positions. So y1, they asked us to find this earlier. So when we're at the value of 16, what's the value? I'll use a different color, I suppose. When we're at the value of 16, what is our height? When we're at 32, what's the height? And when we're at 48, what is the height of the trapezoid? We found these values earlier, so we'll plug those in as well. 2 times, and this is going to be 9.00 plus 7.63. And I believe this last one was 4.31. So these are the intermediate values. So this was at 16, 32, and 48. 4.71. 4.71. There we go. And we can close our brackets. And just be mindful when you do plug this into the calculator, we have 1/2 times 16, so there's 8, I suppose, times all of this business. So make sure that you have brackets enclosing all of this, because we want to multiply this by 8 in this case. All right, so let's go to the calculator and work this out. All right, going to get a new screen, and let's plug this in. So I'm going to write it exactly as it is. This is going to be 1/2 times 8. And then let's open up a double bracket, because we want to multiply everything. And this was 1 plus 1. And I'd actually encourage you to simplify some of this within these brackets beforehand, and then just multiply this, or this should be 16 rather, our interval, the size of our intervals, and then multiply it by what's on the outside. So 1 plus 1 plus 2 times, then we had 9 plus 7.63 plus 4.71. All right, we want to make sure that this is multiplied by everything, so we've got this bracket right here, enclosing everything, and there we go. 357.44. Is that correct? 1 plus 1, that's good. Plus 2 times 9 plus 7.63 plus 4.71 multiplied by 8. This looks good. All right, so going back to our document, we know that the area is approximately equal to 357.44, or to 3 significant figures, 357, I think it's centimeters squared. This is just a model. Where is it? Millimeters. Millimeters squared. IB doesn't really assess units, or if it's not stated, they won't. Sometimes they'll ask you to. And units do come in. They are important when you're asked to convert, but generally when stating your answer, you can just write the value itself. All right, so that's the trapezoid rule. Here's the explanation of the trapezoid rule, and you can always use this approach as well if plugging into the formula is a little confusing. So when we're talking about a trapezoid, we have something like this. I'll try to write it in the corner right here. So trapezoids usually are represented flat, kind of on the base. And then this would be one parallel side, this would be the other. We would call this A and B, and then this would be the height of the trapezoid. What we're doing when we're using the trapezoid rule, we're rotating this trapezoid on its side. And let's put this a little closer. And we have that exact same trapezoid, but in this case, if we're rotating at 90 degrees, the height here is h, this long side is b, and this is a. And the area of a trapezoid, if we're looking at a and b here, is just going to be the average of these two parallel side lengths, so a plus b over 2, the average of them, and then multiplied by the height. And so, if we're trying to use the trapezoid rule, what we're doing, in essence, is we are making an approximation of the area under the curve using trapezoids. So if this is our first, let's say, segment, or if we want to have 4 intervals, we have one trapezoid with a height of 1, and then a height of 9, we said. And then we have another trapezoid. When it's 32, our height is 7.63. And then another trapezoid, let's actually put that in, 7.63, and then we have another trapezoid at 48, which is 4.71, And then finally, one more trapezoid all the way here, again with this height, since we are flipping it on its side with a height of 16. So h is actually the same throughout. It's the base once we flip it, but if we imagine our trapezoid on its side, it's the original height. And so we can use the trapezoid to find, let's say, the area of this, which is just going to be 1 plus 9 over 2 times 16. And this would be 9 plus 7.63 over 2 times 16. And this would be the average of these two, 7.63 plus 4.71 over 2 times 16. And this last one, running out of space a little, 4.71 plus 1 over 2 times 16. And if you were to add each of these up, so this plus this plus this plus this one over here, you would get that same 357. It just takes a little longer. All the formula is that condensed, where this is the size of the intervals. So our size of the intervals right here, traveling a distance of 64, breaking it up into 4 pieces. This is the height at the beginning. This is the height at the end. You see in our original trapezoid rule, we just had this multiplied by, we only had this as part of one trapezoid, and the end point is also just part of one trapezoid. And then we have 2 times, and then these intermediate values, these intermediate heights. And you see we actually have this as part of one trapezoid, and then it's also part of this trapezoid. So we multiply it by 2, and this we multiply by 2, and this we multiply by 2. So those intermediate heights. So there's really 2 different ways we could use the trapezoid rule in some sense. We can use the formula, or essentially we could find the area of each of the individual trapezoids and then add them all together. So A1, A2, A3, A4, and so on. A1, A2, A3, and A4. All right, so once you become familiar with the trapezoid rule, it's not all that bad. And to be honest, these kind of questions, they do have a similar structure. I think you'll see another one on an earlier paper where they have the same structure. Use the trapezoid rule, and then it'll be followed up by find the actual area under the curve, and then how accurate is this estimate. Use the calculate the percentage error. All right, so find Jan's estimate for the area of the cross-section. We did that. Now, part C, write down the integral that Jan can use to find the exact area of the shaded part of the cross-section. So we want to write an integral. That means we're talking about our sum of the area under the curve. So the sum of some function that we can use to find the exact area of the shaded part. All right, so this is C1. So this is our integral essentially up here. And it might look a little intimidating, but let's work it out. So this we can think of as the sum. And then we have our starting points and our ending points. So this is the start, this is the end, and then we have our function. And then in the IB, in AISL, it's always in terms of dx, but really you just want these to match. And so this thing right here, this f of x, is just our function, the thing we want to find the area under. So let's go write that out and fill in the blanks. I'm going to move this just a little. That's fine, actually. So if we want to find the area under the curve, we know we started at 0. That was our starting point right here. And our ending point, we went all the way to 64. So 0 to 64. And what was our function? Our original function was 4 root x minus x over 2, I believe, minus x over 2 plus 1. And then we want to write this in terms of dx. And that's it. That's our area, or that's our integral for the area under the curve. Okay, hence use your graphic display calculator to find the area of the shaded part of the cross-section. Give your answer correct to 1 decimal place. Okay, so that's important. Be an unfortunate way to lose a mark. Let's take a look. So we've got the integral. Let's go to the calculator screen and work this out. All right, let's get a new calculator screen. So in this case, we want to go Menu, Calculus, and we want to find the numerical integral. And here we go. We're starting at 0, going up to 64, and we want to find the sum. That is to say, the area under the curve of this function, which is defined as 4 root x minus x over 2 plus 1. And then we want to match this variable, so it's in terms of dx. All right, 405.333. So let's go back to the document and let's write this out. So what is the area under the curve? It's equal to 405.333. They asked us to write it to 1 decimal place, so just 405.3. Okay. All right. This looks good so far. So let's keep going and let's see what we can do. Calculate the percentage error of Jan's estimate or Jan's estimate, I'm not sure. Jan's estimate in part B. Okay. So this is part 2, I suppose, part 2 and 3. Here we have D. So percentage error, find the percentage error. This is actually given to us in the formula booklet as well. So let's go back and have a look. This is right actually at the beginning of the formula booklet. Under number and algebra, I believe. So I edited this up from earlier. Here we go. Under number and algebra, we have 1.6 percentage error. Right at the bottom, percentage error is equal to estimate minus exact over estimate times 100%. So let's go back. We'll write it out and explain what's going on. So we have percentage error is equal to, and then we have these absolute value signs. I'm actually going to write it out in words. Estimate minus exact over exact. And then we want to write this as a percentage because it's percentage error. And what these things, they're called absolute values. What they do is they say no negatives. So even if you get a negative value, we don't want any negatives. We want to write it just as a positive difference. We want to find what's called the magnitude of the difference between our estimate and our exact. So percentage error is equal to, our estimate was 357, our exact value was 405.3, and we want to say what fraction is that out of our exact value. We want to times it by 100%. Okay, so let's go back to the calculator screen and work this out. Okay, so we can use absolute value if we wanted to, but let's just write it out, and if there's a negative, we'll ignore the negative. So here we go. Let's write it out. We can write it out as one big fraction, I suppose. 357 minus 405.3 over 405.3. And this actually is going to give us as a negative. It's giving us to us as a decimal. Let's multiply by 100. And we'll press enter here. And so we have 11.9%. Remember, we don't want any negatives. The absolute value takes away the negative for us. We don't want to deal with any kind of negatives. So we just have 11.9%. Okay, let's go back to the document. Here we go. Percentage error is just going to be, let's write this as 11.9%. Okay, good so far. All right, question 2 is 15 marks. Let's see what we can do. Ansel is designing a racing track for a local bicycle club. The following diagram shows an incomplete portion of the track. Ansel wants to design the track such that the inner edge is a smooth curve from point A to point B, and the other edge is a smooth curve from point C to point D. So smooth kind of curve from point C to D and from A to B. So it wants to complete this bicycle track. The distance between point A and point B is 90 meters. To create a smooth curve, Ansel first walks to point M. So here he is, he's walking to point M. Write down the length of BM. So BM is going to be, use a different color, BM is going to be this distance right here. And so if 90 is the total, halfway through is just 45 meters. Okay. Alright, and likely we're going to need to make use of that. Ansel then walks 32 meters in a direction that is perpendicular to AB to get from point M to point E. Point E is the center of a circle whose arc will form the smooth curve between A and B on the track as shown in the following diagram, and it's down here. Okay, so let's mark that up actually. We found that the distance from B to M was 45, and we were told that he walks a perpendicular distance of 32 meters. So perpendicular will just be a right angle. Right? Alright, so we know this is a right angle. It's perpendicular, and he's walking 32 meters. Okay, now we want to find the length of BE right here. So the line segment BE. Let's go ahead and work that out. Since we have a right angle triangle here, we should be able to use the Pythagorean theorem. And let's call this, let's call it x for now. Let's call it actually, don't want to over-determine or over-define our variables. But let's just call it x. I think that should be fine. So what do we know? Our Pythagorean theorem, I'm going to throw around the variables a little. Our Pythagorean theorem is a squared plus b squared equals c squared. And this actually is not given in the formula booklet, but if we have some right angle triangle, and this is A and this is B, this is our longest side. So what we're saying is the square of the two shorter sides, if we sum them or add them together, it'll equal the square of the longer side. And our hypotenuse is always the longest side. So let's go ahead and work that out to find the length of BE. So we have 45 squared plus 32 squared, and that should equal to, in this case we called it x, so let's write it as our unknown, our x squared. Okay, we can end solve this, or we can just essentially take the square root of all of this, and then that will be equal to x. So both will give us the same answer. Let's go ahead, so it's a little unclear, let's go ahead and put this into the calculator. Alright, so we have 45 squared plus 32 squared, and then we want to take the square root of the answer, or of all of that, is 3049. And it gives us 55.2178, or 55.2. So let's go back to the document and work this out. So we have this. It is equal to 55.2 to 3 sig figs. The next question, we're asked to find BEM. So what is BEM referring to? We start at B, we go to E, then we go to M. So we're asked to find this angle right here, this theta value. Okay, so BEM. Since we have a right angle triangle right here, we should be able to use SOHCAHTOA, or just our trig ratios. So once again, we have SOHCAHTOA. Any of these should work, but since we have this as an exact, this 45, we have the opposite, and we also have this given as an exact value. This 55.2 we actually found out using Pythagorean theorem. Might be a little inaccurate, shouldn't matter, but we have the opposite, we have the adjacent side. So opposite, adjacent, let's use tan. So let's go ahead. Tan theta is equal to opposite over adjacent. Tan theta is what we're solving for. Tan theta is equal to opposite over adjacent. And we can work this out using a little algebra. And if you want, of course, you can write it out as theta is equal to tan inverse 45 over 32. Or we can, of course, just end solve for theta. Okay, let's, what can we do? Let's go to the calculator screen. Actually, I'm actually just going to work it out on the calculator that I have beside me. And that should be okay. Tan inverse 45 over 32. And it gives us a value of 54.58, or we'll write theta is equal to 54.6. 54.58 is 54.6 to 3 sig figs. Just remember when you're doing these, especially at the beginning of an exam, make sure you are in degrees and not radians. So degrees in the top right corner of your calculator. Okay, moving on. Let's go to part C. Hence find the length of AB. Okay, so the length of arc AB rather. I'm going to clear away some of this and just write what's essential. All right. So what do we know? We know that this theta value was equal to 54.6 degrees. And if we want to find the arc of AB, we want to find this angle, or sorry, not this angle, this length that we sweep through, this portion. This is given to us in the formula booklet. I'm going to write it out here, however. This is arc length. Arc length, if we know if we have a full circle, our circumference, or essentially the perimeter of our circle, is given by 2 pi r. But if we only have, let's say, a portion of this circle, and let's say this is the center, and we only have a portion of our total circle, the question is, well, how much of our circle, if we want to just find the circumference, how much do we have? Well, we know a full rotation is 360 degrees. So if we're talking about the arc length, we only have, well, a portion, theta over 360. We've only swept through a portion of that 360 degrees. So arc length is theta over 360 times the circumference, a full rotation. But we don't have a full rotation. We have a partial rotation. So find the length of arc AB. What do we need to solve for? We need to find r and theta. We already know we have this value, 54.6. So if this is equal to this side length right here, and this side length right here, because this was the midpoint. So we know that this, sorry, we also know that this is the midpoint, and this is the midpoint, so these two are the same. And since they share this side, we actually have two equivalent triangles. So if this side length right here is 54.6, we know that this as well will be equal to 54.6 degrees. So in sum, what angle do we sweep through? What fraction of a whole do we have? Well, we have 54.6 times 2. So if we wanted to find this whole theta value, let's just call this 54.6 times 2. 54.6 times 2 is given to us by 109.2. That's correct, yeah. So this whole angle that we sweep through is 109.2. Alright. So we've got this part, 109.2 over 360. That's a portion that we've swept through, portion of our circumference, I guess, that we're dealing with. And then we want to multiply this by 2 pi, and then r. R is our radius. So remember, we're sweeping through this angle, and this distance from the center to the edge of our circle is going to be our radius. So we know that the radius is equivalent to 55.2. There it is. That's our radius as well. So 2 pi times 55.2. Okay, that should give us our arc for AB. Let's go into the calculator and find the value. Okay, so we have 109.2 over 360, and we want to multiply this by 2 times pi. Oops, sorry, we don't need that. 2 pi, and then the radius we said was equal to 55.2. Okay, and this would be our arc length, 105.206. Let's go back to the document. So 105.206 to 3 sig figs will just be 105. Okay, let's keep going. The outer edge of the track from C to D is also a circular arc with center E, such that the track is 4 meters wide. Calculate the area of the curved portion of the track ABCD. Alright, so outer edge of the track from C to D is also circular. So from C to D, this is also a portion of a circle, and the track itself, the width of this track is 4. And we're asked to find the area of the track. That is to say, this portion of the track right here. So the total area right here. This is what we want to solve for. Okay, so that's kind of an interesting question. So we just had arc length. Now we're asked to find the area not just of a sector, not just of a fraction of a circle, but we're asked to find this portion right here. So we want to find this right here. So the question is, how can we essentially find that? Let's draw a diagram and see what we can do. So here is a circle. And if we have just a portion of a circle, let's say here's our center, then we have a portion of a circle, that would be the area of a sector. So area of a sector. Area of a sector for some theta, so some portion of a circle. So we know again, to sweep out a whole circle would be 360 degrees. But we don't have a whole circle, we just have theta over 360, a portion. And the total area of a circle is given by pi r squared. Area of a sector is given to us in the formula booklet as well. And so in this case, we want to find not just a sector, we want to find a fraction of a sector, which makes it a little more challenging. But if we imagine that this is this green area that we want to solve for, and we have this blue area right here, what we can do is we can find the area of this larger sector. I'm going to highlight it. So we can find the area of this larger sector, but we don't want all of it. We want only what's within. So what we can do is we can take this area out on the inside. So let's say the area of the green, which is the larger sector, let's call it area of the green, minus the area of the blue would give us just the area of, let's just call it the track, I guess, the area of the track. So how do we find the area of this blue section right here? Area of this blue section, we have, actually sorry, let's find the area of the green first. I think that'll be better. So we have this larger track right here. Let's find the area of this larger track. Area of a sector is given by pi r squared times theta over 360. we're still sweeping through an angle of 109 degrees. So for the area of the green triangle, it's going to be still 109.2 over 360 times pi, and then what is the radius? So the radius of this smaller circle was 55.2, and how do we find the area, or sorry, the radius of this larger circle? Well, we know the track is itself 4, so if we're traveling 55.2 from here to here, and we travel another 4 meters to complete this radius, we would travel 55.2 plus 4, or you would travel a total distance of 59.2. So pi r is 59.2 squared, pi r squared, minus, and the area of the blue sector is again going to be 109.2 over 360. So the portion that we've swept through is 109.2 degrees. Actually, I don't know why I wrote 109.2 instead of 109. Generally, we want to preserve as much accuracy as possible. And since they never asked for 109.2, and they just asked for this 54.6, generally we want to preserve as much accuracy as possible. So 109.2 is actually not a bad idea. Okay. 109.2 times pi, and then the radius is, we already found it to be 55.2. This is the radius of the green, and this one right here is the radius of the blue. Okay, so it's going to be 55.2 squared, and all of this should equal the area of the track. So we've got some sector, but we don't want the whole sector. We want to subtract a portion out of that. So we can find the area of the larger sector, which is this green one right here. This larger green one, which includes the blue, right? Which includes the blue. And then what we're going to do is we're going to take the blue portion out. We're going to remove this, which is given by this formula right here. Okay, so it looks kind of intimidating, but conceptually I don't think it's going to be too bad. We've got a slice of a circle, only a part of our circle, and we want to remove a section of that part itself. So larger area minus smaller area to find what remains. Okay, so let's go to the calculator screen and work this out. Okay, so let's set a fraction up, 109.2 over 360. We're going to multiply this by pi, and then the radius itself for this larger one was 59.2. We want to square that, and we want to take away the smaller circle. The smaller circle as well was 109.2 over 360 multiplied by pi, and then the radius of this was just 4 meters less. Okay, and that should give us our area, 436.07 meters squared. So let's go back to the document. So the area of the track is then equal to 436.07, or just 436 meters squared. Okay, not too bad. Calculate the area of the curved portion of the track. I'm going to write it here because I believe we'll need it later. 436 meters squared. Alright, last part of this question. The base of the track will be made out of concrete that is 15 centimeters deep. Calculate the volume of concrete needed to create the curved portion of the track. So we want to find the volume, and it's going to be 15 centimeters deep. What's going on here? And let's see, why is it a 3-mark question? So here we've got the track itself, right? So we've got this curved portion of the track. And what we want to do is we want to pour some concrete within this track. So let's say I've got something like this. I'll do my best to potentially draw this curved portion of the track. We want to pour some concrete along here. I think that's okay, I guess. And what we want is we want the concrete itself to be, if this is the height, I think I can actually do a better job. I'm going to try to do a slightly better job of this diagram because I think it may be important. Okay, so we've got this volume. Volume is, of course, just going to be our... Oh my goodness, what is going on? What is going on? That's fine, I suppose. So we've got this portion of our track, and this is part of our track right here. And this is, of course, a little accentuated, but if we know the area of our track, and we want to, this is just a section of it, and we want to have a volume of 15 centimeters, volume itself is just length times width times height, or area of the base times height. So if we already have the area of the base, we should be able to just multiply it by the height and be done. But why is this a 3-mark question? Our track itself has an area, so the area of the track has an area of 436 meters squared, but, and this is where, not exactly a trick, but maybe where close reading matters, this is given to us in centimeters. So sure, volume is simply equal to area of the base times height, but the area of the base is 436, and it's in meters, and the height itself is in 15 centimeters. So we need to convert our centimeters to meters. We know there's 100 centimeters in a meter, so 15 over 100 means that we only have 0.15 meters. So there we go, 0.15. And that should give us our volume. Area of the base times height. We know the area of the base of this track, and we want to stack it up with 0.15 meters of concrete. Okay, I'm going to work that out on the calculator that I have beside me. And we have it as 65.4 meters cubed, so cubic meters. All right. So maybe kind of a tricky question. Yeah, I suppose this 3-mark is some indication that there's something more going on than just area of the base times height. Even so, 3 marks might be a little high. So convert your 15 centimeters into meters. And just so this is clear, 100 centimeters is equivalent to 1 meter. And so if we have 15 centimeters is equivalent to what? Well, what can we multiply? Actually, let's ignore that kind of. Let's keep it as 100 centimeters is equivalent to 1 meter. Okay. Next question, 18-mark question. The running time T minutes of 200 family movies are recorded in the following table. So we have this group frequency table here. And we want to write down the mid-interval value of T is greater than 70 and less than 80. So first off, what's going on here in our group frequency table? Group frequency table breaks up a total sample into class intervals. So what they're saying here from this T is greater than 70, less than 80, is we have 11 movies, and their runtime, or the length of the movies, we have 11 movies between 70 and 80 minutes, and 51 movies between 80 and 85 minutes, and 68 between 85 and 90, and so on. First question, they're just asking, write down the mid-interval value of 70 and 80. So when T is greater than 70, greater than or equal to 70 and less than 80. The mid-interval value is essentially the midpoint, the halfway point. And the mid-interval value of 70 and 80 is 75. So we can just find the average between the two. Calculate an estimate of the mean running time of the 200 movies. So let's see what we can do there. For this question, remember the IB often will present one question that will then kind of scaffold or give you a cue of what's coming next. So the first question, we had to find the mid-interval value, and we'll actually make use of that. That should be a kind of cue in terms of how to approach the rest of this question. So we have 200 movies, and we want to find the mean running time, or the average running time or length of these movies. And we don't know the length of the individual movies because they're already grouped together. So just looking at this first one here, where we have 11 movies between 70 and 80, and the mid-interval value of 75, we can look and we can ask ourselves the question, what is the average length of these movies? And it's possible that the movies are, let's say, 78 and 79 and 77, and they're all clustered towards the higher end. But what we're imagining is that these movies are roughly evenly distributed. That is to say, there's a 71, a 73, maybe a 75 and a 79, but on average, if we were to take these 11 movies, the average runtime would be roughly 75 minutes. And same thing for this 51 minutes right here. We don't know the lengths of the individual movies, but on average they're 82.5, and same here for these 68 movies. This is 87.5, 92.5, and this last one, the average would be 100. Okay, so these are all the mid-interval values of these movies, or the average runtime. And that's going to help us if we want to find the overall average of these 200 movies. So what is our average? How can we find the average? To be honest, there's actually an easier way using spreadsheets, but calculate an estimate of the mean running time of the 200 movies. A 3-mark question sounds like they're going to want to see some process. So the average, which we can also call x bar, is equal to the sum of all values. So we're taking up every single runtime of all of these movies, adding the length of each of these movies, sum of all values, divided by in this case, the number of values. So in this case, the number of movies. So the number of values. Maybe this is a little hand-wavy of an explanation. The sum of all the values. We add up the lengths of all the movies, and then we divide by the total number of movies, and that'll give us the average. So if we want to find the average, we can use these mid-interval values. So there's 11 movies, and the average runtime was 75. And for here, we had 51 movies, and the average runtime of these movies was 82.5. We had 68 movies, and their average runtime was around 87.5, and so on for these 47 movies. And lastly, for these 23 movies, on average, they were about 100 minutes. And altogether we had 200 movies. And so let's find the average running time of these 200 movies. So let's go back to the calculator for a sec. So 11 times 75 plus, I'm going to work out the numerator and then the denominator, 82.5 plus 68 times 87.5 plus 47 times 92.5 plus 23 times 100. And this will be the lengths of all the movies added up. And we had 200 movies, so we'll take this and we'll divide it by 200. So this is every single movie, and we've added up the total length of all the movies combined, and we want to divide it by the total number of movies. This tells us that the average length of these movies is 88.15. So let's go ahead and write that in. 88.15. 88.15, or to 3 sig figs, 88.2. Okay, this is a 3-mark question, and I believe that's the way that they're kind of nudging or suggesting that you solve it. I think there's actually an easier way, so I'm maybe not a big fan of this question because often you want to use most efficient means. Here's another way to possibly solve it. So we can go to spreadsheets, and we'll set up X and Y for the movies, and we'll put our mid-interval values in: 75, 82.5, 87.5, 92.5, and 100. And then we'll put the frequency here. So there were 11 movies that had an average of 75, 51, 68, 47, and 23. In this case, we've got the runtime of these movies and then the frequency. So let's go ahead and try to find the average this way. Let's do stack calculations. And although we have 2 columns, we just have 1 variable. We just have runtime. That's the only variable. We don't have runtime as a function of a number, orders of popcorn or something like that. We're not comparing these 2 things of runtime and snacks that were ordered. We just have runtime, so just 1 variable. X, we placed in the X, and the frequency, we did have a frequency, the number of movies we placed in Y. And let's go ahead and find it out. And here it is. There's X bar, that's our average again, 88.15. Okay, so potentially a more efficient way, or potentially a quicker way as well. But if it's 3 marks, it looks like they want you to write out the mean formula. Okay, let's go back to the document and go on. All right, so we have this table is used to create the following cumulative frequency graph. Use the cumulative frequency curve to estimate the interquartile range. Okay, so interquartile range, I believe this is actually given to you, it is given to you in your formula booklet. Interquartile range, IQR, is equal to Q3 minus Q1. So if we have, let's say, a box and whisker plot, for example, this is often where they're presented. Then we have, let's say, the median right here, and then the whiskers all the way to the max, and then the min. The IQR is the distance from Q1 to Q3. This is our interquartile range. So let's find Q1 and Q3, and then we'll subtract and find the distance between these 2. So remember, our box plot divides everything up into quartiles. So 25%, essentially 25% in each of these quartiles, or it divides our data set up into 4 equal quarters. So if we have 200 movies here, we want to find the value where we have where this marks where 25% of the movies will be less than this. And this Q3 will signify a point where we have 75% less than this individual point. So let's go ahead. 200 movies, let's find for Q1, let's find the 25th, or that first quartile. And this is going to give us a value of 50. So we want to find the point where 50 movies are, or the point where the runtime of the movie that is greater than 25% of the other movies. In this case, 25% of 200 is that movie ranked 50 out of the 200. So let's see, this is 81, 82, 83, and this would be 84. So we know that Q1 is equal to 84. And let's find Q3. Q3 is going to be given by the 75th percentile, the movie or the runtime that is greater than 75% of the other movies. And this is going to give us a value of 150. Here we go. Important to bring a ruler, especially when the margins are pretty small. So this is actually 91. This is going to be 91.5, it looks like. This is 91.5. So Q3 is equal to 91.5. Okay. Let's see, use a cumulative frequency curve to estimate the interquartile range. So interquartile range, Q3 minus Q1, and this is going to give us a value of 7.5. Okay. And kind of guess what's coming next. Starfeud is a movie in the data set and its running time is 100 minutes. Use your answer to part B to estimate whether Starfeud's running time is an outlier for this data. Okay, so if we have, let's draw one other box and whisker really quick. I can do a little better than that. So if we have another box and whisker, for example, and this is our interquartile range, let's set a median right here, and we have these whiskers. And the whiskers often extend to the max or the min. This would be, let's say, the min. This would be the max. But there are points in which there are data values that may lie beyond the main cluster of data points. And so the main cluster, or the central part of our let's say our data point, are clustered in this middle 50%, or what we call the IQR. And the question we're asking here is there a data point that lies far away from our main cluster of data? And how do we determine how far is too far? Well, if we're asking the question of, do these whiskers extend to reach this major, or sorry, one of these points on the outside? So, and these whiskers will extend 1.5 times the IQR. And if it's beyond that, if it's beyond 1.5 times IQR above Q3, or if it's 1.5 times IQR below Q1, then it's considered an outlier and it doesn't reach to this extreme point. So we know our IQR in this example right here was 7.5. And the question that we're asking is, okay, if we know Q3 itself is 91.5, this is equal to 91.5. These whiskers, which are going to extend 1.5 times IQR, are they long enough to grab this outlier, or is the outlier too far? Is it outside of the bounds of the main cluster of data? So let's write that out. Q3 plus 1.5 times IQR. Q3 is Q3 is 91.5, and 1.5 times IQR is 7.5. So I'm going to work that out on the calculator that I have right here. 1.5 times 7.5 plus 91.5 gives us a value of 102.75, or to 3 sig figs. I guess we could say 103, but actually let's keep the values as they are. 102.75. So is this Starfeud, which is 100 minutes, is it an outlier? Justify your answer. In this case, we could write 100 is less than 102.75. And since it's less than our maximum extreme point, we would say no, it's not an outlier. It's not an outlier. And this right here would be a justification. because this is our potential maximum point and it's within that range. It's less than this 102.75. Okay, so a little more here. Let's see what we have. Still in the realm of statistics and probability. It's believed that the running times of family movies follow a normal distribution with mean 88 minutes and standard deviation 6.75 minutes. So key hint already, we're in the realm of normal distributions, and they give us a mean of 88 minutes, standard deviation 6.75 minutes. It's decided to perform a chi-squared goodness of fit test on the data to determine whether the sample of 200 movies could have plausibly been drawn from an underlying distribution. That is to say, is this set or this sample of movies that we've gathered together, can it be modeled by a normal distribution where we have a mean of 88 and a standard deviation of 6.75? And that's the question. So part D asks us to write down the null and the alternative hypothesis. So let's go part D. We have a chi-squared goodness of fit. So we have two chi-squared tests. One's goodness of fit, one's independence. Independence test is blank is independent of blank. That's always our null hypothesis. And the alternative is blank is not independent of blank. But it's dangerous to confuse independent chi-square independence with chi-squared goodness of fit. Chi-square goodness of fit is asking whether our distributions match. And in this case, we have a normal distribution. And we want to see, is the runtime of these movies approximately normal? That is to say, if we have some mean at 88, do we have a situation where we have a major cluster within one standard deviation, and so on and so on? And that's the question. Does this fit a normal distribution? And the null hypothesis would then be runtime of family movies. Runtime can be approximated or modeled by a normal distribution, or the alternative is that runtime is not approximated or modeled by a normal distribution. All right, so that would be our null and alternative hypothesis. Potentially they might ask, and I think they actually do in this mark scheme, by a normal distribution with, and then we might want to say, sorry, this is a little messy, with mean of 88 and standard deviation of 6.75. In this case, potentially more detail. Just putting that at the end. All right. As part of the test, the following table is created. Okay, so runtime less than 80 minutes. What we observe is there 11. What we would expect is 63.6. So we would expect a certain percentage of our 200 movies to be less than 80. And we can find these values using our normal distribution. So let's go find this value of A right here. And it's between this interval of 85 and 90. What that means is, if we have this normal distribution centered at a mean of 88, the runtime of, let's say, movies that are 85 all the way to, let's say, 85 to 90, something like this, we can find the percentage of movies that we would expect to have within this range of 85 to 90, so it's not 90%, just minutes rather. and we can find the percentage of movies that we would expect. And if we know we have 200 movies altogether, we can find out how many movies we would expect to have within this range. So let's go back to the calculator to try to work this out. So menu, probability, we're in the realm of distributions, and we want to use normal CDF. So the lower bound is going to be 85. Our upper bound is going to be 90. Our mean in this case is 88, and our standard deviation is 6.75. And so we're asking, what is the percentage, what are the percentage of movies that fall within this range of 85 and 90? And since it's continuous data, minutes, we don't need to put 84 or 91 for this. We just put the bounds themselves. All right, and we have 0.288 or 28.8%. So let's go back to the document and work with that. So we have 28.8% is how much we would expect. 28.8% of our values we would expect to fall within this range. And that's not actually the value that we put in, because we have 200 movies, and we would expect 28.8 or 0.288. Might as well put some of the other digits as well, just to make sure we get accuracy. But 3 is potentially okay. Generally, you want to save as much accuracy as possible until you get to the end of the question. So roughly 28.8% of our 200. I'm going to work that out on the calculator that I have here. And so we would expect, for A, we would expect 57.6 movies for A. So A is equal to 57.6. And for B, B is going to be 95 and above. So we'll get a different color. What they're asking here is, okay, if a movie has a runtime of 95, what is the percentage of movies that are going to fall within this 95-minute runtime and above? So let's go back to the calculator and work this out. Okay. Menu, probability, distributions, normal CDF. Lower bound is 95. Upper bound for this, we can put 1,000, or if you want, you can put a very high number. 1,000 should be okay. 500 should be okay. Just want to make sure that you grab all of the movies that are to the right. Mean of 88, standard deviation of 6.75, and there we go. So 0.149859, roughly 14.9%. Let's go back to the document. Okay, so I'm going to use the same color of red. 0.149859. I'm going to multiply this by 200, so roughly 15% of 200. I'm going to keep all the decimals, just because we're not at the end of the answer. It's only at the end that we round to 3 sig figs. 9859 times 200. And we have 29.97, which we can round to 30. So B is equal to 30 movies. Okay, that looks good. All right, let's see what we can do from here. EI, or part 1 of E, sorry. Find the value of A and B. We did that. Hence perform the test to a 5% significance level, clearly stating the conclusion in context. So we want to run a chi-square goodness of fit. We've got our values, and observed and expected. Let's go ahead and run the test. So going back to the calculator for a sec, let's get a new document, just because we used variables before. Go into spreadsheet. for this, going to write observed and expected. You can always use x and y, and it should be okay. So let's put in our observed values and the expected values. 23.6, 42.1, 57.6, 46.7, and 30. Okay. Got our observed and our expected. Let's run a statistical test. And we will do chi-squared goodness of fit. Observed, we called O, and expected degrees of freedom. What are degrees of freedom? Let's go back to the document for a sec. So as part of process, especially for an 8-mark question, we would almost certainly want to show degrees of freedom. Degrees of freedom for a chi-squared test, goodness of fit or independence, is equal to rows minus 1, columns minus 1. For a goodness of fit, we're always just going to have 2 columns here. So essentially it's always rows minus 1, but just for simplicity's sake and ease of memory, I suppose, we can always just use this. So rows, we have 1, 2, 3, 4, 5. 5 minus 1, and then 2 minus 1. If we want, we can write this. Degrees of freedom is 4. Okay. So let's go back to the calculator screen. Degrees of freedom is 4. Let's press OK. And we have a chi-squared value and a p-value. P-value of 0.016469. Okay. So let's go ahead and go back to the document. So what do we know? We have a p-value which is equal to 0.0165, I guess. And we had a significance level, I believe it was 10%, 5% significance level. So clearly stating the conclusion in context. So what we can write is we can write 0.0165, or what this is also equivalent to is 1.65%, multiplying this by 100 to just make it a percentage. And we can say that this is less than 0.05, this 5% above, or we can write this out. Either way should be okay. And our p-value is equal to 1.65. It's less than the significance level. Remember, a kind of intuitive way to remember this is just the probability that the null hypothesis is true. And 1.65% is very, very slim chance. We needed 5% or more to say that, hey, maybe the null hypothesis is true. In this case, 1.65%, very, very small chance that the null hypothesis is true, very small chance that we see these kind of results just based on probability alone. So in this case, we would reject, or sorry, better to write is fail, oh no, sorry, in this case we just reject. Reject the null hypothesis, or H naught. Reject the null hypothesis, and in context we could say that runtime does not follow a normal distribution. Runtime does not follow a normal distribution with a mean of 88 minutes and a standard deviation of 6.75. Okay, not bad. Okay, going on, looks like we have a financial mathematics question here. Ruben wants to buy a car for a price of 285,000 South African Rand. He goes to a bank to get a loan to buy the car. To be eligible for the loan, Ruben must make an initial down payment equal to 25% of the price of the car. The bank offers him a 5-year loan. So a 5-year loan for the remaining balance with a 4.5% nominal interest rate per year. We're compounding it monthly and compounded monthly. Ruben will pay the loan in fixed payments at the end of each month. Find the original amount of the loan after the down payment is paid. Give the exact answer. So he wants to take out a loan for $285,000, but the bank won't just give him the total sum without any kind of down payment. I guess they maybe want to see if he's solvent or financially secure, or they want at least something. Car's going to lose value. Worst comes to worst, they're going to need to repossess the car. If they get 25%, then they're a little bit more insured on this loan, or this kind of risk that they're taking. So they say, hey, can you give us 25% down payment first? Okay. So the first question is find the original amount of the loan after the down payment is made. So he wants to take out $285,000, but he's not going to take out, the bank isn't going to give him that whole $285,000. They're going to give him what is left over after he pays 25%, or 1/4, or 0.25 of that $285,000 loan. This is also equivalent to saying that we just want 25% removed, so we only want 75% of this $285,000. And so if we work this out, we'll get $213,750. Part 2, calculate Ruben's monthly payment for this loan to 2 decimal places. Okay, so to 2 decimal places. Alright, so since we're making monthly payments, we'll need to use the financial solver. We can't use compound interest formula or anything like that. We're going to need to use the financial interest solver. Finance solver. So let's go ahead and write down each of the values here. So N, I, our interest rate is a percentage, present value, payments that are made, the final value, and payments per year, compounding periods per year, and then we have when is the payment being made, which is often at the end. Alright, so let's go ahead and see what we have. So first one is often the easiest, that's just interest rate. He's paying 4.5%. In the end, we want to find out the monthly payments that are being made. So PMT is what we're trying to solve for. The present value of the loan is, in this case, the loan that he has received from the bank. He didn't take out the whole $285,000. The bank has just given him $213,750 rand. And we keep this as positive because this is money that he has in hand. This is money in the individual's possession. The final value of the loan is going to be 0, and he is going to pay it off over 5 years. We'll need that. Payments per year, he's making 12 payments per year, and the compounding rate is compounded monthly, which means it's compounded 12 times a year. Payment is being made at the end of the year, and so we just need to find out the number of payments, which is linked to payments per year. So 5 years, and he's paying 12 payments every year, so this should be equal to 60. Alright, let's go to the calculator screen and work this out. Menu, where are we now? Finance solver. 60 payments, interest rate is 4.5%. He took out a loan of $213,000. We don't know the payments. Final value wants to be equal to 0. Payments per year, 12, and all looks good. And so this is the size of his payments, $3,984.94 or 95 cents in this case. All right, let's write this out in the document. So in this case, we have, this is a negative, which means that the money is flowing out actually. So it's money that's leaving his pocket in some sense. On the final answer that you would put down, you wouldn't need to write negative. So monthly payment is equal to, let's just write that, monthly payment equal to 3,984.95 Rand, to 2 decimal places. All right, using your answer from part A2, calculate the total amount Ruben will pay over the life of the loan to the nearest Rand. Do not include the initial down payment. This is a pretty common question, and it's not actually all that bad. So if we think that he is paying $3,984.95 every month, and he's making 60 payments, the total amount that he is paying over the life of the loan, that he will pay over the life of the loan, is just going to be 60 payments of 3,984.95 Rand. Let's go ahead. Actually, I'm just going to use a calculator that I have here. 4.95. All right. So he is paying $239,097. Okay. Ruben would like to repay the loan faster and increases his payments such that he pays 4,600 Rand each month. Find the total number of monthly payments he will need to make to pay off the loan. Okay. 2-mark question. So we can actually use a lot of what we have here. So I'm actually going to copy it, and we'll use it on the other screen right here. Okay. So let's go ahead. Whoops, that's a little small. All right. So what is going to change? We don't know how many payments he's going to make. The payment itself has increased. So let's see. I'd like to repay the loan faster. His payments are now 4,600. This is still the initial size of the loan. He's paying now 4,600. We want to put a negative because it's money flowing out of the individual. So to distinguish that, we put a negative. Okay, find the total number of payments. And to be honest, I think that's it. Everything else stays the same. Initial loan, the payment amount is just different, and now we want to find or solve for n. So let's go back into the calculator screen and let's edit this finance window. And we don't know how many payments. Present value is all the same. He's going to be paying 4,600. Final value is going to be 0 still. PPY, CPY, everything else looks good. So number of payments is 51.15. Okay, that's interesting. Find the total number of payments he will need to make to pay off the loan. Okay, so let's go back to the document. Part C. Let's just write number of payments is equal to, so we said 51.15. If he makes 51 payments, he hasn't yet paid off his loan. It's not until he makes 52 payments. The bank wouldn't accept a fraction of a payment. Let's say, what would it be? 15% into the month, so maybe 4 days into the month or so. It wouldn't exactly be it. He would finish his total loan, or he would complete paying off the loan at 52, after 52 months, after 52 payments. So the final answer would be 52. The total number of monthly payments that he'll need to make. All right. Let's go to question D. This strategy will result in Ruben's final payment being less than 4,600 Rand. Determine the amount of Ruben's final payment to 2 decimal places. And this is a 4-mark question, which seems like, or suggests that it should be a little challenging. And it kind of is. It really is. All right. Determine the amount of Ruben's final payment to 2 decimal places. What can we possibly say? So, after 51 payments, he hasn't yet paid everything off. So, he won't yet have finished paying off the loan. And if he makes a total of 52 payments of 4,600, he'll have overpaid a little. So there's 2 strategies that we can use. And I'll show you them both, actually. So let's use this once again. I hope that grabs everything. Oops. Okay. Copy. So this is part D right here. Okay, so this is a new question, and let's see if we can modify this. Things are going a little funny now. Here we go. So let's say this is him paying off 4,600. It should still be negative, but let's say he pays off. Let's say he makes 52 payments. What is the final value? What is the final value? We'll be able to see how much he has overpaid by. So in this case, just to expand on this, let's say he does make 52 payments of 4,600. This is still the size of the loan. This is still the interest. This is still how many payments he's making a year, and so on. And compounding period. What would be the final value? That should give us the amount that he's overpaid by. So let's go into the calculator screen and try to work that out. So this should be 52, 4.5. And let's ask the question, how much has he overpaid by? And here we go. So going back to the calculator screen, our final value is equal to 3,893.20. Okay. So that would be how much he has how much he has in his pocket, how much he has overpaid by. And imagine we have this last month, the 51st month. He's come close to paying everything off. He pays off a full 52, so he pays one whole extra month, and it's 46,000. But he looks into, let's say, his bank account where his loan was, and it's not only at 0, it's at $3,893.20. And the question is, how much was his final payment? So if he has $3,893.20 in his account, and he was only required to pay $4,600, what was that last payment? What is the difference between the two? So if we say 4,600 minus 3,893.20, which is how much he has in his bank account, that's how much he overpaid by. He only needed to pay, just subtracting one from the other, did it on the calculator that I have beside me, 706.8 ZAR, or South African Rand. That's how much he overpaid by, or sorry, that's not how much he overpaid by. This is how much he overpaid by. That's how much he needed to pay. So once again, this 706.8 is how much he needed to pay, or 80 rather. This is how much he did pay, and he found in his bank account that he had some extra money. Okay. To be honest, that's actually the easiest way to work it out. I'll show you the other way. It's a little more challenging, to say the least. So here it is. I'm actually just going to clear this screen and erase this as well. Okay. So let's imagine this other situation where he pays 51 payments and he doesn't quite get to this 51.5. what would be the final value that he has remaining to be paid. So let's go to the calculator screen and work this out. So in this case, we imagine that he's only paid 51 payments. Everything else is the same. What is the final value? And we see it's 704.156. So let's go back to the calculator screen. Back to the document for a sec. And we see the final value that he needs to pay is 704.16, let's say, 156, so 16 to 2 decimal places. And you might be thinking, hey, you know, that's a little funny. How can these both be correct? And they're not. This one is the correct answer. So what happens with this 704.6? Why is it like that? So at the end of the 51st month, he still has $704.16, but he's going to make one more payment. And what is the size of that payment at the end of the month that he needs to make? It's not 704.16 because the bank is still charging interest. Bank is still charging 4.5% compounded annually. So this is where it gets a little challenging. We can use the financial solver, or we can use this. Final value is equal to present value 1 plus r over 100 times k, number of compounding periods, n times k, so number of years. Or in this case, number of months in this case. Or number of, rather, compounding periods. So the present value, he owed $704.16. It's 4.5% interest, 12 compounding periods, and in this case, he just wants to pay for 1 month. And then this is k, so n times k. This is actually just 1 month, so let's just leave it like this. So $704.16, and then the bank is going to charge him not 4.5% interest, but 4.5% interest divided by 12, so a 12th of that 4.5%. Then if we work this out, I'm going to work it out on my calculator here. 704.16 times 1 plus divided by 12 gives us 706.8006. So we can write 706.80. I think that's a more challenging way to work it out. This is potentially the most intuitive way, and it's kind of, I think, the trap, saying, okay, 51 months, what's left that he needs to pay? But the thing is, the bank is still charging interest on the remaining amount. So even though he just has 1 month left, the bank is still charging him 4.5 over 12, 1 plus. They're still charging him, whoops, let me actually change this. They're still charging him 4.5% over 12. Sorry, that's not right either. They're still charging him. Actually, no, sorry, that was correct. 0.45 over 12. They're still charging him this fractional amount of interest. All right. Okay. Last question, and let's see what we can do. All right. Mosaic Industries is an international company that sells cell phone cases. Their market research predicts that the average number of cases they will sell each month can be modeled by the equation. So number of cases that they'll sell can be modeled by this equation, where x represents the selling price in euro of each case. So we have a function, number of cases we sell, as a function of the price per cases. A salesperson suggests that Mosaic Industries should sell their cases for 16 euros each. Find the average number of cases this model predicts Mosaic Industries will sell. So let's work this out. number of cases is given by 20,000 minus 1,000 times the price per case. So this looks like it's just going to be an input-output kind of question. Our price per case was 16, so let's input that price of 16 and see how many cases. And this should give us 20,000 minus 16,000, give us 4,000 cases. Not too bad for a 2-mark question. Calculate Mosaic Industries' average monthly income before any expenses at the selling price. Okay, so income is total amount that the company would earn before expenses. Often we call this gross revenue. So income is going to be made up of, well, not just the number of cases. The total amount this company will earn that they will have flowing in as kind of gross revenue will be made up by the number of cases they sell multiplied by the price per case. And we know that they're going to sell 4,000 cases, and they're going to sell them at 16 euros a piece. So 4,000 times 16, total income they earn is $64,000. So not too bad. Sometimes it's just a challenge interpreting what the question is asking and then formulating how to go about solving it. Total earnings, total revenue, number of cases times the price per case. Alright, so now we're getting into a little bit of heavier algebra. Hence, write down the function Rx, or revenue, is a function of the sale price, I guess, that can be used to predict Mosaic Industries' average monthly income before expenses at any selling price. So let's go ahead and try to work that out. So we still have this formula right here. The income that they'll earn will still be made up of the number of cases times the price per case. So let's write out this equation. We're going to write out income as R of X. The number of cases that they'll sell is given by this formula right here. So let's substitute that. That's the number of cases. 20,000 minus 1,000x. That's the number of cases. And the price per case, well, they told us that x represents the selling price. And so this would just be equal to x. And that's it. It's not too bad. Okay, I think these are, I don't think this is the final question. I think there's some more further on. So not quite there yet. Mosaic Industries has 10,000 euros of fixed monthly operational costs. Additionally, Mosaic Industries must pay their phone case supplier 10 euros for each case. Calculate Mosaic Industries' average monthly profit if they sell each case at a price of 16 euros. So this is 16, not generalized, but just 16. All right. So profit is equal to income, or gross revenue, minus the expenses that we need to pay. So this is often called net income, total take home, I suppose, after all expenses. And so Mosaic Industries' average monthly profit if they sell each case at a price of 16. So earlier on we had this question where we found out the income at $16 a case, and we found out it was $64,000 in income or gross revenue. So $64,000. But we know they need to pay 10,000 euros in overhead cost, in warehousing or something like that, maybe labor and so on. And we also know they need to pay 10 euros for each case. So 10 euros, and then how many cases were sold. So 10 euros for every single case. We sold 4,000 cases. So 10 euros times 4,000. All right. And then we can hope for Mosaic Industries that this is positive. So 64,000 minus 10,000 minus 40,000. And this will give us a value of $14,000. Okay. Show that the average monthly profit for any selling price x can be found by the function p of x is equal to negative 1,000 x squared plus 30,000 x minus 2010. Okay. So profit is still given by income minus expenses, and we do have a formula for profit already. Or sorry, for income rather. The generalized form for income is $20,000 minus 1,000x times x. That was how much gross revenue. $20,000 minus 1,000x times x. That was what we had up here, this revenue that they earn. Okay. They're still going to need to pay $10,000, and the other expense is going to be the number of phone cases, or sorry, the price per case, which is $10. Selling price x can be found by, and then the number of cases that will sell. So the number of cases that will sell. How could we write that out? Okay. This is the number of cases is actually just given by this right here. This is our number of cases. So we can write that just as 20,000 minus 1,000x. Okay. And that looks to be it, actually. So how many marks is this question? It's just a 2-mark question, actually. If you wanted to be absolutely sure that this whole long expression turned into this, you'd need to expand it. And actually, I'll expand it right now, but if you're not sure how to expand it, this is just distribution. So if we have x times, let's say, 20,000 minus 1,000x, what we would do is we would multiply the term out in front by every term on the inside. So x by 20,000 would give us 20,000x, and this would give x times 1,000x, would just give us 1,000x squared. And then we can do that for all of these. So x times 1,000, or negative 1,000, x times 20,000. This becomes what we found out before, 20,000x minus 1,000x squared, still minus 10,000, and then we're going to multiply once again. This is going to be, in this case, 20,000 times negative 10. It's going to be 200,000. Got to be careful here. This is negative 10 times 20,000. This is negative 10 times negative. So this is actually going to turn into a positive 10,000x. Okay, so let's go ahead and get our x squareds. This is negative 1,000x squared. Are just plain x's. So there's an x, there's an x. We're going to have 20,000 plus 10,000, or, whoops, 30,000x. And then we have 200,000 plus 10,000, or sorry, negative 200,000 minus another 10,000 would be subtracting a whole $210,000. And there it is. Okay. If that one was a little challenging, remember we have kind of discrete parts of a paper too. So even if this one was a little confusing, question F, or part F, is kind of encapsulated in itself. So here they're asking us for part F to find p prime of x, or the derivative. This prime, remember, is the derivative. So let's find p prime of x. So we know that p of x is equal to negative 1,000x squared plus 30,000x minus 210,000. In your formula booklet, you have the derivative. So if we have some function f of x and it equals some variable raised to the power of n, f prime of x, or the derivative, what does it require us to do? We take the exponent, multiply it out in front, so then it would become nx, and then we reduce the exponent by 1, n minus 1. And that's in your formula booklet. So let's go ahead and apply that here. This is x raised to the power of 2. Let's multiply out in front, and then we have negative 2,000. X used to be squared, now it's just to the power of 1. Whenever we have an x, the x's just go away. You can think of it as x to the 1, and it's used up its only power in some sense. And now it's x to the 0, and anything to the power of 0 just becomes 1. So now we just have plus 30,000. And constants themselves just go away. So this would become 0. Alright. That looks good. That is our derivative. Show that the salesperson's selling price does not maximize their average monthly profit. Okay, so 2 parts to this question. It doesn't ask you to make use of the derivative. Sorry, I should put a prime there. It doesn't ask you to make use of the derivative. Nope, I'm sorry, there should be a prime here. So we can actually just graph this function. But if we wanted to use the derivative itself, it's not too bad actually. So let me just provide a little bit of conceptual background. So if our original function looks like this, our derivative is also called our slope function, and what it'll do is it'll find the slope of the function at any given point. So the slope of the tangent line. So if we want to find the slope at this given point, it'd be something like this, except it wouldn't be curved. It'd be something like this. And if we wanted to find the slope at this point, be something like this. And then after if we wanted to find, let's say, this point right here, it would be something like this. And if we wanted to find the slope of the line at this point, that would be what our gradient function, our derivative, would do for us. And we see we're having increasing slope, increasing slope, increasing slope, but there's going to be one point on this function where we move from increasing to decreasing, and that's going to be a point where we have a slope of 0, and that's going to be where p prime of x, where the derivative itself is equal to 0. So after we're done increasing, before we start decreasing again, there's going to be a point where it's exactly flat. And so to solve this part 2 right here, just using the derivative, we could just say, okay, well, what's the point where p prime of x is equal to 0? Or when does this whole derivative equal 0? And you can solve it that way. But if you want, you could also just graph the original function right here and find the maximum. For visual sake, I'm actually going to graph it, and that's how we'll solve it. Okay, so let's go to the calculator screen and let's graph the original function. So menu, haven't needed to use this at all actually for this exam, which is a little surprising. Negative 1000x squared plus 30,000x minus 210,000. 1000x plus 30,000x minus 210,000. This is going to be very, very large. So let's hope that zoom fit will help. And it's not actually too bad at all. Zoom fit doesn't do too poorly. Let's zoom out a little more. And that's not bad. I think we can do everything that we really need to just with this. We could change the bounds a little, but I think it's okay. Let's find the max. Analyze graph, maximum, and there it is. So once we sell once we price the phone cases at $15, we have a maximum profit. And we'll explain what this is, or this 1.5 E plus 4. So let's go back to the original document for a sec and find the maximum. So I'm going to put the graph underneath again. And this actually would count for process. They would want to see a sketch. And here's our function right here. Here's our maximum point. And our calculator gave us this, 1.5e plus 4. And that's not really acceptable for the IB, or they wouldn't really like that. So what is this 1.5e plus 4? This e is just times 10, and then this 4 is to the 10th power. So when we see 1.5e to the 4, what this is saying is 1.5 times 10 to the 4. Or, if we have 1.5, let's move 1, 2, 3, 4 hops. So they earn $15,000 in gross profit. Profit as a function of the price of a phone. And there it is. So we'd want to change this if we wanted to write this as process marks. So let's just say 1.5 times 10 to the 4. So how can we show that the salesperson's selling price does not maximize their average monthly profit? Well, we saw that the maximum profit occurs when we price our phones at $15. Alright. Final 2 questions, and I'd imagine this should be a good challenge. Mosaic Industries negotiates a new deal with their phone case supplier. Under the new deal, the supplier agrees to discount the cost of each case based on the number of cases purchased by Mosaic Industries. The cost charged by the supplier for each case can be found using the function. So cost as a function of the number of cases is equal to $10, but now we are subtracting a fraction of a cent for the total number of cases. Or sorry, the total number of cases, where n represents the number of cases sold by Mosaic Industries. Find the function that can be used to find Mosaic Industries' average monthly profit using the new deal from the supplier. So average monthly profit using the new deal from the supplier. Okay. So what was our profit function before? It used to look like this. And it was, I'm going to use a different color here. This was, this was the income before. This was just the overhead cost, like the warehouse, the kind of the base kind of overhead cost that we needed to pay, or that Mosaic needed to pay. And this was the cost per phone, and this was the number of cases. And so our cost is no longer $10. Actually, I'm going to grab this. Hopefully it'll grab just this part. Okay, and we'll copy this, and we'll edit it down here. Okay, clean it up just a little. So this is still much the same, but we're going to change just parts of this. So profit, this is still the same. This is their income. This is the fixed costs. This is the fixed cost, the overhead. And then they had this final value. And this, remember, was the cost per case. And this right here, I'm going to clean it up. This was equal to the number of cases. Number of cases. And so the only thing that's changed is that the cost per case is no longer $10. It's 10 minus 0.001 n. Income that we make is still the same. It's number of cases times the price per case. Fixed cost remains fixed, but the cost per case now changes. So I think there's more complicated ways to work this out, but otherwise I see it this being the most straightforward way. 20,000 minus 1,000x times x minus 1,000 minus, now our cost per case is $10 minus 0.0001, and then n is the number of cases. n is the number of cases. This is what our number of cases is. It's given by, it's getting a little cluttered, I apologize. This is the number of cases. So $10 minus, good question. $10 minus 0.0001 times the number of cases, which is given by 20,000 minus 1,000x. So that's a good challenge. 0001 times 20,000 minus 1,000. Jeez. 1,000x. That's the cost per case. $10 minus $10 minus, this is the cost per case. The cost per case is $10 minus 0.001, 20,000 minus 10x. And this is the number of cases. So really running out of space here. 1,000x. Okay. Wow. Here is the income. This is number of cases, price per case, fixed costs, minus right here the cost per case. And it's $10 minus a fraction of a cent for every single case that they sell. And this is times the number of cases. Wow. Okay. All right. I mean, sure. It's a good question. It's a good question. There it is. I think potentially it's possible to simplify things a little, especially up here when we substitute this 10 minus 0.001 times 20,000. We could simplify that because 10 minus 0.001 times 20,000 would just be 2. And 0.001 times negative 1,000, negative times a negative would be positive, and this would be just 0.1x. So if we just multiply this value times this value, and then that again simplifies. 10 minus 2 is 8 plus 0.1x, and this would be the cost per case. So, I mean, this last question has taken quite a while. We could rewrite this if we wanted to. 20,000 minus 1,000x times x minus 10,000 minus, and this is our cost per case, 8 plus 0.1x cost per case times the number of cases. And I guess it doesn't look as bad where that, it still looks pretty bad, but as intimidating. Okay. Find the function that can be used to find Mosaic's average monthly profit using the new deal. And there it is. We're good. By the way, we can leave it like this. Just looking at the mark scheme on, I'll bring it up actually here. Here it is. Here's the mark scheme. We can leave it just as that. We don't need to expand and then write it in some clean form. It looks like the IB or examiners will accept this value right here. Okay, so let's return to the main document that we're editing right now and go on to H. H says, hence find the selling price per case that Mosaic Industries should choose in order to maximize their average monthly profit under the new deal. Okay, so in this case you might want to simplify it because this is going to be a lot to put in the calculator. I'm actually going to do it. I'm going to multiply it out just to see how you can possibly do it. Again, we'd want to expand. And so this would be, I'm just going to work this out as quick as I can, I suppose. 20,000 x minus 1,000 x squared. This is still minus 10,000. And then we have what's called binomials. So we need to multiply this by this and this by this. So 8 times 20,000. Ooh, I'm starting to have second thoughts here. 8 times 20,000 would be 160,000. 8 times negative 1,000 is going to be negative 8,000 x. This is going to be 20,000 would just be plus 2,000 x. So right now I'm multiplying 0.1 times 20,000, 0.1x times 20,000. And then 0.1x, and this would be negative 100x. Since there's a negative out in front, right here, it would turn everything to a positive. So what I'm actually going to do is just remove the brackets. To save some time, I'm going to remove the brackets, and everything that was a positive, I'm going to turn to a negative, and everything that was negative, I'm going to turn to positive. Now we got a group like terms. If you're still around watching this part, negative 1,000 x squared. Now we have our x's. 6,000, this would be 26,000 x. And the last little bit, negative 16,000 plus 10,000 would be negative 170,000. All right. To find the maximum selling price under the new deal, this is our profit. Let's graph this function and solve. Okay, gonna get a new screen. Let's go into add graphs. Let's, I was almost tempted to use the original one just to see if it would work. I'm wondering if it will. 200,000. Actually, we did all that expansion. Let's go back. 1,000 x squared plus 26,000 x minus 170,000. 1,000 x, 26,000 x. Good. Let's go ahead and hopefully zoom fit will work. That's not bad again. And it just looks like potentially, I hope nothing has gone wrong, but let's see. Zoom in. Let's see if I entered this incorrectly. Negative 1,000 x squared plus 26,000 x minus 170,000. Let's see. Okay, let's find the maximum. Oh, hence find the selling price per case that Mosaic Industries should choose in order to maximize their average profit. Okay, let's find the maximum. Analyze graph. Maximum, what is it? No, this can't be right. This says that they're losing money under this new deal, but that doesn't make sense. Let's see. I see. Okay, so it looks like something went wrong in the addition. So let's go back to the document. Okay, so we had, this is where it is, we had negative 1,000 x squared, and then, okay. So, I mean, kind of tricky. When we multiply this 0.1x by negative 1,000, it comes to 100 x squared. And if we have positive 100 x squared and negative 1,000 x squared, altogether we have negative 900x squared. So once again, 1000x squared, expanding 0.1x times 1000, negative 1000x squared, gives us this negative times a negative turns into a positive. Positive 1000x squared, positive 100x squared, minus 1000x squared gives us 900x squared. So let's go back to the document. Let's edit this and write this as 900. And there we go. There's our new max, 14.4. So I'm going to go back to the document just about there. Profit as a function of selling price. Again, we get a quadratic. Here's our maximum, and it says 14.4. And when that happens, we have 1.78 times 10 to the 4, or 1, 2, 3, 4, roughly $17,800. And this should be all right as a process right here. Find the selling price per case that they should choose to maximize their average monthly profit. 14.4 to get $17,800. Okay, everybody, that's about it. I hope it was helpful, and I wish you the best of luck. Okay, bye-bye.